All right, this is CS50, and this is the end of week 2. So today we're going to continue our look at how we represent things underneath the hood, moving away from numbers like integers and floating point values and focusing on strings and ultimately more interesting programs. But we'll also take a look at a couple of domain-specific problems, the first of which will be involving cryptography, the art of scrambling information. And what you see above here is a picture of radio orphan Annie's secret decoder ring from yesteryear. This is actually a very primitive form and child-friendly form of cryptography, whereby this ring has 2 disks, one inside and one outside. And by rotating one of those, you can essentially line up letters like A through Z with other letters like B through A. In other words, you can literally rotate the alphabet, thereby coming up with a mapping from letters to letters, so that if you wanted to send a secret message to someone like Annie, you could write down your message and then rotate the letters, whereby if you mean to say A, you instead say B. If you mean to say B, you instead say C, or something a little more clever than that. And then ultimately, so long as Annie has this decoder ring, she can decode the message. Now, you may recall, in fact, that this was used in a very famous film that plays ad nauseum during the Christmas season. Let's take a look here.
Be it known to all and sundry that Ralph Parker is hereby appointed a member of the Little Orphan Annie Secret Circle and is entitled to all the honors and benefits occurring thereto.
Signed, Little Orphan Annie. Countersigned, Pierre Andre, in ink. Honors and benefits already at the age of 9. Come on, let's get on with it. I don't need all that jazz about smugglers and pirates.
Listen tomorrow night for the concluding adventure of the Black Pirate Ship. Now it's time for Annie's secret message for you members of the Secret Circle. Remember, kids, only members of Annie's Secret Circle can decode Annie's secret message. Remember, Annie is depending on you. Set your pins to B2. Here is the message. 12, 11,
I am in my first secret meeting.
25, 14, 11, 18, 16.
Oh, Pierre was in great voice tonight. I could tell that tonight's message was really important.
3, 25. That's a message from Annie herself. Remember, don't tell anyone.
90 seconds later, I'm in the only room in the house where a boy of 9 could sit in privacy and decode. Aha, B. I went to the next. E. The first word is B. S. It was coming easier now. U. 25. That's R.
I'll be right there, Ma! Gee whiz.
T. O. Be sure to. Be sure to what? What was little orphan Annie trying to say? Be sure to what?
Annie has got to go. Will you please come out?
All right, Ma! I'll be right out!
I was getting closer now. The tension was terrible. What was it? The fate of the planet may hang in the balance.
No! Annie's gotta go! I'll be right out! For crying out loud!
Gee, almost there. My fingers flew. My mind was a steel trap. Every pore vibrated. It was almost clear. Yes, yes, yes,
Be sure to drink your Ovaltine. Ovaltine? A crummy commercial? Son of a bitch.
So that then is a glimpse at what cryptography can be for this drink from yesteryear. So a quick announcement: if you are free this Friday at 1:15 p.m. and would like to join us for CS50 lunch, head to this URL here. First come, first served as usual, but over time we'll make sure that most anyone who'd like to participate may schedule-wise. So strings. We have Zamila, whom you've now met most likely in problem set 1, whose name is spelled thus. And suppose you typed her name into a computer program that's using something like getString in order to retrieve those keystrokes. How do we go about representing a string, a word, a paragraph, or multiple letters like these here? We talked last time about integers and problems that arise with integer overflow, and floating point values and problems that arise with imprecision. With strings, we at least have a bit more flexibility, because strings just in the real world can be of pretty arbitrary length, pretty short, pretty long. But even then, we're going to find that computers can sometimes run out of memory and not even store a big enough string. But for now, let's start to visualize a string as something in these boxes here. So 6 such boxes, each of which represents a character, or char. So recall that char, C-H-A-R, is one of the built-in data types in C. And what's nice is that you can use that sort of as a building block, a puzzle piece, if you will, to form a larger type of data that we'll continue to call a string. Now, what's useful about thinking about things like strings in this way? Well, it turns out that we can actually leverage this structure to actually access individual characters in a pretty straightforward way. I'm going to go ahead and create a file called string0.c, but you can call it whatever you'd like, and on the course's website is already this example in advance, so you don't need to type everything out. And I'm going to go ahead and first do int main void, and within a few days we'll start to tease apart what void is here, why it's int next to main, and so forth. But for now, let's continue to copy paste that. I'm going to declare a string called s, and I'm going to return from getString whatever the user types in. This is going to be a simple program, no instructions. I'm just going to blindly expect that the user knows what to do to keep it simple. And now I'm going to have a for loop, and inside of my for loop, I'm going to have int I gets 0. And I is, again, just a convention, an index variable for counting, but I could call this whatever I want. I'm going to do I is less than, well, Zamila's name is 6 letters long, so I'm going to hard code that there for now. And then I++. And now inside of these curly braces, I'm going to do printf, and I want to print one character at a time. So I'm going to use %c for perhaps the first time. And then I want to print each character on its own line. So I'm going to put a little \n there, close quote. And now I want to do something here. I want to print out the specific letter in the string s as I'm iterating from 0 on up to 6. In other words, I want to print the ith character of s. Now, how can I do this? Well, much like the boxes in this representation here kind of conjure up the notion of boxing letters in, you can similarly do that syntactically in C by simply specifying I want to print out s's ith character using the square brackets on your computer's keyboard that on a US keyboard are generally above your return key. So this isn't quite right yet, as you may have noticed, but I'm going to kind of blindly forge ahead here, and I'm going to do make string 0. But before I do this, let's see if we can't anticipate some common mistakes. Is this going to compile? So no, I'm missing a whole bunch of things. Libraries, I heard. So which header files might I want to add here? Yeah. Excellent. So I need standard I/O for what purpose do I want standard I/O? For printf. So include standard IO.h, and you also propose that I include the CS50 library for what reason? To have string. So we'll see what CS50's library is doing to create this notion of a string, but for now you can just think of it as an actual data type. So that seems to be a little cleaned up, and now I'm going to go ahead and indeed do make string 0. Compiled, so that's good. So /string 0. Let me zoom in so we can see more closely what's happening. Enter. ZAMYLA, enter. And we've printed out Zamila's name. So that's pretty good. So now let's go ahead and run this program again and type out Davin's full name. Surprise, surprise. Enter. We have not printed Davin's full first name correctly. Now this should be obvious in retrospect because of what sort of stupid design decision? Yeah, I hard-coded the 6 inside of my for loop. Now, I did that only because I knew Zamila's name was going to be 6 letters, but surely this isn't a general solution. So it turns out we can dynamically figure out the length of a string by calling a function called strlen. Again, deliberately, succinctly named just to make it more convenient to type, but that's synonymous with getting the length of a string. I'm going to go back into my terminal window and rerun the compiler. But it's yelling at me, implicitly declaring library function strlen with type unsigned and I'm lost completely. So especially as your eyes start to glaze over with error messages like this, focus honestly on the first few words. We know the problem is in line 8, as indicated here, and it's in string0.c. implicitly declaring library function Sterling. So that is generally going to be a pattern of error messages, implicitly declaring something. So in short, what have I seemed to have done with respect to line 8 here? What might the solution be, even if you've never used Sterling yourself? Yeah. It's part of a different library. So it is declared, so to speak. It is mentioned in some file other than standardIO.h and CS50.h. Now, where is it defined? To be honest, you either have to just know this off the top of your head, or you Google this and find out, or know this. I've opened up in the CS50 appliance the terminal program, which is just the big full-screen version of what's in the bottom of gedit's window. And it turns out that there's a similarly succinct command called man for manual, where if you type in the name of a function and hit enter, you'll get back fairly arcane documentation. It's just text that generally looks a little something like this. It's a little overwhelming at first glance, but frankly, I'm going to let my eyes glaze over and only focus on the part I care about for the moment, which is this, which looks structurally like something I'm familiar with. Indeed, the man page, so to speak, will tell you in what header file a function like Sterling is defined. So I'm going to go back now to gedit, and I'm going to go ahead and add in here sharp include string.h and save the file. I'm going to clear the screen with Control L, if you've been wondering, and I'm going to rerun make string 0, compiles this time /string 0, Zamila. That seemed to work. Let me go ahead and rerun it with Davenport, enter, and that too seemed to work. So we can do a little better than this, though. We can start to tidy things up just a little bit, and I'm going to actually introduce one other thing now. I'm going to go ahead and save this in a different file. And I'm going to call this file string1.c, just to be consistent with the code you'll be able to find online. And let's focus in on exactly the same code. It turns out that I've been kind of taking for granted the fact that my laptop, and in turn, the CS50 appliance, has a lot of memory, a lot of RAM, a lot of bytes of space in which I can store strings. But the reality is, if I typed long enough and enough keystrokes, I could, in theory, type in more characters than my computer physically has memory for. And this is problematic. Much like an int can only count so high, in theory, you can only cram so many characters into your computer's RAM, or random access memory. So I had better anticipate this problem, even though it might be a rare corner case, so to speak. Doesn't happen that often, could happen. And if it happens, and I don't anticipate it and program for it, my program could do who knows what. Freeze, hang, reboot, whatever. Something unanticipated might happen. So what I'm going to do now, henceforth really, is before I ever blindly use a variable like s that has been assigned the return value of some other function like getString, I'm going to make sure that its value is valid. So I know, only from having read CS50's documentation for getString, which ultimately will point you at, that getString returns a special symbol called null, N-U-L-L, in all caps, if something goes wrong. So normally it returns a string, but otherwise if it returns N-U-L-L, we'll eventually see what that really means, that just means something bad happened. Now this means, much like in Scratch, I can check a condition here and see if s does not equal null. So if you've not seen it before, this just means does not equal. So it's the opposite of equal equals, which recall is different from single equals, which is assignment. So if s does not equal null, only then do I want to execute these lines of code. So in other words, before I dive in blindly and start iterating over s and treating it as though it is a sequence of characters, I'm going to first check, wait a minute, is s definitely not equal to this special value null? Because if it is, bad things can happen. And for now, assume that bad things happening means your program crashes and you can't necessarily recover. So frankly, it looks uglier. It's kind of confusing now to glance at, but this will become more familiar before long. But I'm going to propose now one other improvement. That's an improvement to correctness. My program is now more correct because in the rare case that not enough memory exists, I will handle it and I'll just do nothing. I at least won't crash. But let's do a final version here in a file called string2.c. I'm going to paste that same code for just a moment, and I'm going to highlight this line 11 here for just a moment. Now, the reality is that smart compilers like Clang could fix this for us behind the scenes without our ever knowing, but let's think about this fundamentally as a problematic design. This line of code is, of course, saying initialize some variable I to 0. That's pretty straightforward. And what, again, is this statement here, I++ doing? We've seen it before, but we didn't really talk about it. incrementing I. So on every iteration through this loop, every cycle, you're incrementing I by 1. So it gets bigger and bigger and bigger until the loop terminates. How does it terminate? Well, there's this middle condition, which we've used before. You've seen in walkthroughs in the P set. But what is this saying? Do the following loop so long as I is less than what? The length of the string. So it translates pretty cleanly to English in that sense. Now, the problem is that every time I iterate through this loop in theory, I'm asking this question. Is I less than the string length of S? Is I less than the string length of S? Now, which is I changing on each iteration? It is, because of the plus plus. So every iteration, I is getting bigger. But is S getting bigger or smaller or changing at all? No. So in terms of design, one of the axes along which we try to evaluate code in the class, this feels kind of stupid. Like you are literally, on every iteration of this loop, asking the same damn question again and again and again, and literally it is never going to change, at least if I'm not touching S and trying to change the contents of S. So I can do a little better than this, and what I'm going to do is not declare just one variable I, but a second variable. I'll arbitrarily, but conventionally call it n, assign n equal to the string length of S, and then over here I'm going to do a clever little optimization, so to speak, that at the end of the day is no more correct or no less correct than before, but it's a better design in the fact that I'm using less time, fewer CPU cycles, so to speak, to answer the same question, but just once. So any questions on that general principle of improving, say, a program's efficiency? Yeah? Good question. So why do we put the plus plus on the end of the I instead of the beginning of the I? In this case, it has no functional impact. And in general, I tend to use the postfix operator so that it's a little more clear as to when the operation is happening. For those unfamiliar, there is another statement whereby you could do plus plus I. These are functionally equivalent in this case because there's nothing else around that incrementation, but you can come up with cases in lines of code in which that makes a difference. So generally, we don't even talk about this one because, frankly, it makes your code sexier and sort of slicker and more fewer characters. But the reality is it's a lot harder, I think, even for me to wrap my mind around it sometimes. It's the order of operations. So as an aside, if you really don't like this, even though this is kind of sexy looking, you can also do I plus equals 1, which is the uglier version of the same idea for postfix incrementation. I say this, and you should make fun of it, but you will come to see code as something beautiful before long. Right? Okay, yeah. Question in the middle? You do not need to say int n. So because we have already said int, you do not need to say it again. The catch is that n has to be the same data type as I. So that's just a convenience here. Yeah? Absolutely. So %c, recall from last time, is just a placeholder. It means put a char here. \n, of course, just means put a line break here. So that just leaves now this piece of new syntax. And this is literally saying, grab the string called s and go get its ith character, so to speak. And I keep saying ith character because on each iteration of this loop, it's as though we are printing out first s bracket 0, as a programmer might say, then s bracket 1, then s bracket 2, then 3, then 4. But of course, it's a variable, so I just express it with I. Key, though, is to realize, especially if you've not been acclimating to this world of programming where we all seem to count from 0, got to start counting from 0 now. Because strings, first character, the z in Zamila, is, for better or for worse, going to live at location number 0. All right, so let me bring us back here to Zamila and see what's really going on underneath the hood. So there's this notion of typecasting. And you might have actually played with this already, maybe for the hacker edition of PSET 1. But typecasting just refers to the ability in C and some other languages to convert one data type to another. Now, how might we see this pretty straightforwardly? So this, recall, is the beginning of the English alphabet. And the context, recall, from like a week ago is ASCII, the American Standard Code for Information Interchange, which is just a really long way of saying a mapping from letters to numbers and from numbers to letters. So A through M here, ... lines up with, recall, the decimal number 65 on up. And we didn't talk about this explicitly, but surely there's similar numbers for lowercase letters, and indeed there are. The world decided some years ago that little a, lowercase a, is going to be 97, and little b is going to be 98, and so forth. And for any other key on your keyboard, there's going to be a similar pattern of bits, or equivalently a decimal number. So the question at hand then is, how can we actually see this underneath the hood? So I'm going to go over to gedit again, and rather than type this one from scratch, I'm going to go ahead and just open up something from today's code called ASCII 0. And ASCII 0 looks like this. So let's wrap our minds around this. So first, I've commented the code, which is nice because it's literally telling me what to expect. Display a mapping for uppercase letters. And I don't quite know what I mean by that, so let's infer. In English, maybe somewhat techie English, what does line 18 appear to be doing for us? Just line 18. What's it inducing? What's it going to kick off here? A loop. And how many times is that going to iterate? Not 6 times. 26 times. Yeah, sorry. 26 times. Why? Well, it's a little weird, but I've started counting from 65, which is weird but not wrong. It's not bad per se. And I'm doing that only because for this example, I'm kind of anticipating that capital A was 65. Now, this is not the most elegant way to do this, to kind of hard code esoteric values that no one is ever expected to remember. But for now, notice that I'm doing this up through 65 plus 26, because apparently I don't even want to do the arithmetic in my head, so I'll let the compiler do it. But then on each loop, in each iteration of the loop, I'm incrementing I. So now, this looks a little cryptic, but we should have the basic building blocks with which to understand this. %c is just a placeholder for a char. %i is a placeholder for an int, and it turns out that by using this new syntax, this parenthetical, so to speak, so a data type inside of parentheses, I can force the compiler to treat I not as an integer, but as a char, thereby showing me the character equivalent of that number. Now, down here, this code is pretty much identical. I just wanted to make super explicit the fact that I'm starting at 97, which is lowercase a, on up through 26 more letters. And I'm doing, again, casting I, so to speak, or typecasting I, so to speak, from an int to a char. So the end result is going to be, frankly, information we already know. I'm going to make ASCII 0.c. Notice you probably made that mistake as I just did accidentally. Make ASCII 0. Now I'm going to do /ASCII 0. I'll zoom in, and unfortunately it's going to scroll off the screen, but we see an entire chart where A maps to 97, B maps to 98, and if we scroll up further, A, of course, maps to 65. So this is only to say that what we've been preaching, there is this equivalence, is in fact the case in reality. So a quick modification of this. Let me open up ASCII1.c, and notice this clever sort of clarification of this. This is ASCII1.c, and notice this crazy thing. And this really gets to the heart of what computers are doing, even though we humans would not count in terms of letters. I don't start thinking, all right, A, then B, and use those to count physical objects. You can certainly say that I want to initialize some variable called C, but I could have called this anything. So C is initialized to capital A. Because at the end of the day, the computer doesn't care what you're storing. It only cares how you want to present that information. How do you want the computer to interpret that pattern of bits? So this is not something I would generally recommend doing. It's really just an example to convey that you can absolutely initialize an integer to a char, because underneath the hood of a char, of course, is just a number from 0 through 255, so you can certainly put it inside of an int. And what this also demonstrates is that we can convert from one type to another here, ultimately printing the same thing. And in fact, this I will fix online was meant to say this again here. Let me clean this up online, and we'll see in an online walkthrough as needed what was intended there. Okay, so last example now involving A's and B's, and then we'll take things up a notch. So with A's and B's and C's and the capitalization and the equivalence thereof, let's take a look at this example here. Another code example. We'll open one that's already made, so we don't have to type it all out from scratch. And notice in anticipation, we're using multiple header files, among which is our new friend string.h. Now this looks at first glance a little cryptic, but let's see if we can't reason through what's going on here. First, I get a string from the user, and I put that string in a variable called s. Copy-paste from before. In line 22, I'm apparently doing exactly what I did a moment ago. I'm iterating over the characters in S. And the new tricks here are using string length, the minor optimization of storing the string length in n rather than calling Sterling again and again and again, and just checking that I is less than n. Now here things get a little interesting, but it's just an application of this same new idea. What in English does S bracket I represent? Counting each character, and even more succinctly, S bracket I represents what, would you say? Not to put you on the spot here. So if the string is Zamila, which starts... Good. Exactly. This square bracket notation allows you to access each character individually. So S bracket 0 is going to be the first character in the string. S bracket 1 is going to be the second, and so forth. So the question I'm asking here in this condition is what? Is the ith character of S greater than or equal to lowercase a? And what does this mean here with the double ampersands? And, it's just equivalent to this. And is not a keyword in C. You have to use, annoyingly, ampersand, ampersand. And this, conversely, is asking, is S's ith character less than or equal to lowercase z? And again, here's where understanding the underlying implementation of a computer makes sense. Notice that, even though I have the ... over there, looks like A through Z in lowercase are all contiguous values up from 97 on up, and same for uppercase starting at 65. So the takeaway then is that in English, how would you describe what line 24 is doing? Yeah. It's checking whether each character is a lowercase letter. So even more succinctly, is the ith character of S lowercase? That's all we're expressing here logically, a little cryptically, but ultimately pretty straightforwardly. Is S ith character lowercase? If so, and here's where things get a little mind-bending for just a moment, if so, go ahead and print out a character. So this is just the placeholder, but what character? Why am I doing S bracket I minus this expression here? Well, notice the pattern here. The actual numbers don't matter so much, but notice that 97 is how far away from 65? 32. How far away is 98 from 66? Little c from big C, 32. So there's a 32 hops from one letter to another. So frankly, I could simplify this to that. But then I'm kind of hard-coding this low-level understanding that no reader is ever going to understand. So I'm going to generalize it as, I know the lowercase letters are bigger. I know the capital letters are smaller values, ironically. But this is effectively equivalent to saying subtract 32 from S bracket I. So in the context of these letters, if the letter happens to be A, lowercase a, and I subtract 32, what effect does that have mathematically on lowercase a? Capitalizes it. And indeed, this is why our program is called capitalize 0. This program either capitalizes a letter after checking if it is indeed a lowercase letter. Otherwise, in line 30, what do I do if it's not a lowercase letter that I'm looking at a particular iteration in the loop? Just print it out. So don't change stuff that's not even lowercase. Restrict yourself to little a through little z. Now, this is fairly arcane, but at the end of the day, this is how we once upon a time had to implement things. If I instead open capitalize 1, oh, thank God, there's a function called toUpper that can do everything we just did at a fairly low level. Now, toUpper is interesting because it is declared in a file, and you would only know this by checking the documentation or being told, say in class, where it exists, in a file called ctype.h. So this is another new friend of ours, and toUpper does exactly what its name suggests. You can pass in as an argument between these parentheses some character. I'm going to pass in the ith character of S using our fancy new notation involving square brackets, and take a guess. What is the return value of toUpper apparently going to be? A capital letter. A capital letter. So if I pass it lowercase a, hopefully, by definition of toUpper, it's going to return an uppercase a. Otherwise, if it's not a lowercase letter in the first place, I just print it out. And indeed, notice this second friend here. Not just toUpper exists, but is lower, which actually answers that question for me. Now, whoever wrote these things tens of years ago, you know what? Implemented toUpper and is lower using code like this. But again, consistent with this idea of abstracting away sort of lower-level implementation details and standing on the shoulders of people who came before us, using functions like toUpper and isLower, which wonderfully enough are nicely named to say what they do, is a wonderful paradigm to adopt. Now, it turns out that if I read the man page for, say, toUpper, I learn something else. So man toUpper. It's a little overwhelming, but notice here's that mention of the header file that I should use. As an aside, because this is misleading, the function uses ints instead of chars for reasons of error checking, but we'll perhaps come back to that in the future. But notice here, toUpper converts the letter C to uppercase, if possible. So that's pretty straightforward. And now let's be a little more specific. Let's look at the part of the man page under return value. The value returned is that of the converted letter, or C if the conversion was not possible, where C is the original input, which I know from here from the argument to toUpper. So what is the takeaway of this? The value returned is that of the converted letter, or C, the original letter, if the conversion was not possible. What improvement can I therefore make to my code's design? Yeah. I can remove the else statement, and not just the else statement. I can remove the whole fork in the road, the if-else altogether. And so indeed, let me open the final version of this, capitalized 2, and notice just how, if you will, sexy the code is now getting, in that I've reduced from some 7 or so lines to just 4 the functionality that I intended by simply calling toUpper, passing in s bracket I, and printing out with the placeholder %c that particular character. Now, arguably, there is a bug, or at least the risk of a bug in this program. So just to come back to an earlier takeaway, what should I probably also do in this program to make it more robust so that there's no way it can crash, even in rare cases? Yeah. Make sure it's not null. So really, to make this super proper, I should do something like if s is not null, then go ahead and execute these lines of code, which I can then indent like that, and then put in my close brace. So good tying together of the two ideas. Yeah?
Could you use a do-while loop instead?
Could I do a do-while loop? Could you use a do-while loop? Short answer, no, because you're about to introduce another corner case. If the string is of 0 length, if, for instance, I just hit enter without ever typing out Zamila, I'm going to hand you back an actual string, as we'll eventually see, that has 0 characters. It's still a string. It's just super short. But if you use a do-while, you're going to blindly try to do something with respect to that string, and nothing's going to be there.
Well, I mean, if you did, like, do string s get string while s.
Oh, I see. Keep getting a string from the user. So short answer, you could, and keep pestering them to give you a string that's short enough to fit in memory. Absolutely. I just chose not to. If they don't give me the string I want, I'm quitting. I'm giving up. But absolutely, for that purpose, you could absolutely do that. So the libraries, header files that we're now familiar with are these here. Standard IO, CS50.h, string.h, ctype.h, and there are indeed others. Some of you have discovered the math library in math.h. But let me introduce you now to this resource that CS50 staff, Davin and Rob and Gabe in particular, have put together that we'll soon link on the course's website. It's called CS50 Reference, which, just to give you a quick taste of it, works as follows. Let me go to reference.cs50.net. You'll see on the left-hand side an overwhelming list of functions that come with C. But if I care for the moment about something like Sterling, I can type it there. It filters down the list to just what I care about. I'm going to click it. And now on the left, you'll see what we hope is a more straightforward, human-friendly explanation of how this function works. Returns the length of a string. Here's a synopsis. Here's how you use it in terms of the header file and in terms of what the function looks like in terms of its arguments. And then here, returns the length of a string. But for those of you more comfortable, you can actually click More Comfy, and the contents of this page now will change to be the default values of what you get by using the man page. In other words, CS50 Reference is a simplification of man pages by the staff for students, particularly those less comfortable and in between, so that you don't have to try to wrap your mind around, frankly, some fairly cryptic syntax and documentation sometimes. So keep that in mind in the days to come. So here again is Zamila. Let's now ask a question that's a little more human accessible. Thanks to Cheng, who's been printing more elephants nonstop for the past few days, we have an opportunity to give at least one of them away. If we could get just one volunteer to come on up to draw on the screen. How about here? Come on up. What is your name?
Alex.
Alex. All right. Alex, come on up. We're about to see your handwriting on the screen here. All right, it's nice to meet you. All right, so super simple exercise. Bar is not high to get an elephant today. You are playing the role of get string, and I'm going to just tell you the string that you've gotten. And suppose that you, get string, have been called, and the human, like me, has typed in Zamyla, Z-A-M-Y-L-A. Just go ahead and write Zamyla on the screen as though you have gotten it and stored it somewhere in memory. Leaving room for what will be several other words. That's okay. Keep going. Okay, good. So Zamyla, excellent. So now suppose that you, get string, are called again, and therefore I provide you at the keyboard with another name, Belinda. B-E-L-I-N-D-A. All right, and now the next time get string is called, I type in something like Gabe, G-A-B-E. You're really taking to heart random access memory, which just drawing everything completely randomly. Okay, so...
Sorry, my handwriting's bad.
No, that's okay. And how about Rob, R-O-B? Okay, good. So I didn't anticipate you would kind of lay things out in this way, but we can make this work. So how did you go about laying out these chars in memory? In other words, if we think of this rectangular black screen as representing a computer's RAM or memory, and recall that RAM is just a whole bunch of bytes, and bytes are a whole bunch of bits, and bits are somehow implemented generally with some form of electricity and hardware. So that's sort of the layering we've talked about and can now take for granted. How did you go about deciding where to write Rob versus Gabe versus Belinda versus Zamyla?
I just did it in the order that you told me.
And that is true, but where on what governed where you put Belinda's name and Gabe's name?
Nothing.
Okay, so that works, that's fine. So computers are a little more orderly than that. And so when we implement, stay there for just a moment, when we actually implement something like getString in a computer, Zamyla might be laid out pretty much like you did on the screen there. And what is key to notice here, what Alex did, is there is kind of a demarcation among each of these words, right? You didn't write Z-A-M-Y-L-A-B-E-L-I-N-D-A-G-A-B. In other words, there's some kind of demarcation, which seems to be a sort of random spacing between these various words, but that's good because we humans can now visualize that these are 4 different strings. It's not just one sequence of lots of characters. So a computer then, meanwhile, might take a string like Zamyla, put each of those letters inside of a byte of memory, but that memory is much bigger, of course, than 6 characters. There's a whole bunch of RAM, and so henceforth, this grid of boxes is going to represent what Alex just did here on the screen. And now, Alex, we can offer you a blue or an orange elephant from Cheng.
Take a blue elephant.
A blue elephant. So a big round of applause, if we could, for Alex here. Thank you. So the takeaway is that even though the pattern kind of changed over time here on the board, there was this demarcation among the various strings that Alex got for us. Now, computers, frankly, could do the same thing. They could kind of plop strings anywhere in RAM, up here, over here, down here, down here. They could do exactly that. But of course, that's probably not the best planning, right? If I kept asking Alex to get names, probably he'd put some more down here, maybe up here, over here, eventually like over here. But with a bit more planning, certainly, we could lay things out more cleanly. And indeed, that's what a computer does. But the catch is that if the next string I get after Zamyla is something like Belinda, propose where we might write the letter B with respect to this grid. Where would you go? To the right of the A, below the Z, below the A? What would your first instincts be? So below the Z. And that's pretty straightforward, right? It's kind of neat. It's what we do on a keyboard when we hit enter or an email when making a bulleted list of things. But the reality is that computers try to be more efficient and cram certainly as much data into RAM as possible so that you don't waste any bytes, so that you don't waste any screen real estate. And the problem, though, is that if we literally put the letter B after A, how are we going to know where Zamyla's name ends and Belinda's name begins? So you humans just proposed, well, hit the enter key, essentially. Put it down below. Or even as Alex did, just start writing the next name below the previous one, and below that one, and then below that one. That's a visual cue. Computers have another visual cue, but it's a little more succinct. It's this funky character. \0, which is perhaps reminiscent of \n and so forth now, these special escape sequences. \0 is the way of representing 8 0 bits in a row. 00000000. The way you express that is not to hit the number 0 on your keyboard, because in fact, that is an ASCII char. Looks like a number, but is actually a decimal number that represents this circular glyph, this circular typeface. Meanwhile, \0 means literally put 8 0 bytes here for me. So this is somewhat arbitrary. We could have used any pattern of bits, but the world decided some years ago that to represent the end of a string in memory, just put a whole bunch of zeros, because we can detect that. Now that means that no letter of the alphabet can be represented with zeros, but that's okay. We've already seen that we're using 65 on up and 97 on up. We didn't get anywhere close to all zeros. Yeah. No, just casual. So Belinda, in a computer's memory, is actually going to go here. And I've drawn it in yellow just to draw our attention to it. And notice, too, this is completely arbitrary. I've drawn it as a grid. Like RAM is just some physical object. It doesn't necessarily have rows and columns per se. It's just got a whole bunch of bytes implemented in hardware somehow. But if after Belinda I typed in Gabe's name, he's going to end up here in memory. And if I typed in Davin's name, for instance, he's going to end up here. And I can continue to write even more names. Unfortunately, if I try to write a super long name, I might eventually run out of memory, in which case getString is going to return null, as we said. But thankfully, at least in this visual here, we didn't get quite that far. Now, what's nice is that this general idea of treating things as being in boxes is representative of a feature of C and a lot of languages known as an array. An array is another type of data. It's a data structure, if you will. Structure in the sense of it really kind of looking like a box, at least in your mind's eye. An array is a contiguous sequence of identical data types, back to back to back to back. So a string, in other words, is an array of chars, an array of characters. But it turns out you can have arrays of bunches of things. In fact, we can put even numbers in an array. So the form in which we're going to start declaring this data structure known as an array is also going to use square brackets, but these square brackets are going to have different meaning in this context. And let's see it as follows. Suppose that I opened up a new file here, and I save this as ages.c, and I'll save this in my folder here. And now I'm going to go ahead and start typing something like include cs50.h, include standard io.h, int main void, and then inside of here, I want to first have an int called age, and I'm going to use that to get an int from the user for his or her age. But this program is meant to be used by multiple people for whatever context. I've got a line of people. All of them have to type in their age for maybe some, I don't know, competition or event that they've arrived for. So the next person, I need another variable, because if I just do age gets getInt, that's going to clobber or overwrite the previous person's age, so that's no good. So my first instinct might be, oh, all right, if I want to get multiple people's ages, let's do like this is called this age 1, int age 2 gets int, int age 3 gets getInt, and now I'm going to use some pseudocode here, do something with those numbers. We'll leave for another day like what we're doing there, because we only care for the moment about age 1, age 2, age 3. Unfortunately, once I compile this program and put it in front of actual users, what's the fundamentally poor design decision I seem to have made? Yeah? Yeah, I haven't even tried to figure out how many ages do you actually care about. If I have fewer than 3 people here, and therefore fewer than 3 ages, I'm still blindly expecting 3. God forbid 4 people show up, my program just won't even support them. And so this, long story short, is not a good habit, right? I was essentially copying and pasting code and just tweaking the variable names. And my God, if you had not 3 ages, but 10 or 100 or even 6,500 undergraduates, for instance, like this is not going to be particularly elegant code or sustainable. You're going to have to rewrite the program every time your number of people changes. So thankfully, in our actual ages.c file for today, we have a more clever solution. First, I'm going to borrow the construct we've used a few times, this do-while loop, in order to get the number of people in the room. I'm just going to pester the user again and again until he or she gives me a value of n that's a positive integer. I could have used last time's getPositiveInt, but we don't have that for real, so I went ahead and re-implemented this idea. Now down here, this is the new trick. In line 27, as the comment in line 26 suggests, declare an array in which to store everyone's age. So if you want to get not 1 int, not 2 ints, but a whole bunch of ints, specifically n integers, where n might be 3, might be 100, might be 1,000, the syntax, quite simply, is to say what data type do you want, What do you want to call that chunk of memory? What do you want to call the grid that looks like this pictorially? And in brackets here, you say how big you want the array to be. And so earlier when I said the syntax is a little different here, we're still using square brackets, but when I'm declaring an array, the number inside of those square brackets means how big do you want the array to be. By contrast, when we were using s bracket I a moment ago, s, a string, is indeed an array of chars, but when you're not declaring a variable, as with this keyword here, you're simply getting a specific index, a specific element from that array. Once we know that, the rest of this is straightforward. If new, I'm first going to print out what's the age of person number I, where I just say person number 1, person number 2, person number 3. And I'm just doing arithmetic so that, like normal people, we count from 1 for this program and not from 0. Then I call getInt, but I store the answer in ages bracket I, which is the ith age in the array. So whereas last time we were treating these boxes as chars for Zamaila's name and others, now these boxes represent 32 bits, or 4 bytes, in which we can store an int, an int, an int, an int, all of which, again, are the same data type. Now I do something silly like time passes, just to justify writing this program, and then down here, I again iterate over the array, saying a year from now, person number 1 will be something years old. And to figure out that math, I mean, this is not very complicated arithmetic, I just add 1 to their age. Just to demonstrate again this, just as I can index into a string s, so can I index into an array of ages like that there. So, where is this going to be taking us? So we will see ultimately a few things in the days to come. One, all this time when writing your own programs, like Mario, Greedy, Credit, you've been typing the name of the program and hitting enter, and then getting the user's input with getString, getInt, getLong, or the like. But it turns out that C supports something called command line arguments, which is going to let us actually get at words that you type at the blinking prompt after your program's name. So in the days to come, you might type something like Caesar or /Caesar number 13 thereafter, and we'll see how that works. Because indeed, in problem set 2, we're going to introduce you to a little something reminiscent of Ralphie's challenge earlier of cryptography, the art of scrambling information. This, in fact, is very reminiscent of what Ralphie did. This is an example of an encryption algorithm called ROT13, R-O-T-13, which simply means rotate the letters in the alphabet 13 places. And if you do that, you'll see now what is perhaps a familiar phrase. But the way we're going to use this ultimately is more generally. In PSET 2, in the standard edition, you'll implement a couple of ciphers, one called Caesar, one called Visionaire. Both of them are rotational ciphers in that somehow you turn one letter into a different letter. In Caesar, super simple. You add 1, you add 13, or some number up to 26. Visionaire does that on a per letter basis. So Visionaire, as you'll see in the spec, is more secure. But at the end of the day, what you'll be implementing in PSET 2 is that key that you use both for encryption and decryption, referring to the process of turning plain text, some original message, into ciphertext, which is something encrypted, and then decrypting it again. In the Hacker Edition, meanwhile, you'll be tasked with something similar in spirit, where we'll give you a file from a typical Linux or Mac or Unix computer called Etsy Password, which contains a whole bunch of usernames and passwords. And those passwords have all been encrypted, or hashed, so to speak, more properly, as you'll see in the spec. And the Hacker Edition will challenge you with taking an input like this and cracking the password, that is, figuring out what the human's password actually was. Because indeed, passwords are generally not stored in the clear, and generally passwords should be hard to guess. That's not often the case, and what I thought we'd do is conclude with a couple minutes glance at a particularly poor choice of passwords from a film you might recall fondly. And if not, you should rent.
Helmet, you fiend! What's going on? What are you doing to my daughter?
Permit me to introduce the brilliant young plastic surgeon, Dr. Philip Schlotkin, the greatest nose job man in the entire universe and Beverly Hills.
Your Highness.
Nose job? I don't understand. She's already had a nose job. It was a Sweet 16 present.
No, it's not what you think. It's much, much worse. If you do not give me the combination to the air shield, Dr. Schlotkin will give your daughter back her old nose.
No! Where did you get that?
All right, I'll tell. I'll tell.
No, Daddy, no, you mustn't.
You're right, my dear. I'll miss your new nose, but I will not tell him the combination no matter what.
Very well. Dr. Schlotkin, do your worst.
My pleasure.
No! Wait! I'll tell.
I knew it would work. All right, give it to me.
The combination is 1, 2, 3, 4, 5.
So the combination is 1, 2, 3, 4, 5. That's the stupidest combination I ever heard in my life. That's the kind of thing an idiot would have on his luggage.
Thank you, Your Highness.
What did you do?
I turned off the wall.
No, you didn't. You turned off the whole movie.
I must have pressed the wrong button.
Well, put it back on. Put the movie back on.
Yes, sir.
Let's go, Arnold. Come, Gretchen. Of course, you know I'll still have to bill you for this.
Well, did it work? Where's the key?
It worked, sir. We have the combination.
Great. Now we can take every last breath of fresh air from planet Druidia. What's the combination?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yes.
That's amazing. I've got the same combination on my luggage. Prepare Spaceball 1 for immediate departure.
Yes, sir.
And change the combination on my luggage.
That's it for CS50. We'll see you next week.
And now, Deep Thoughts by Davin Farnham.
Coding in C is so much harder than Scratch. Printf, Scratch was a lie.